Hello friends, welcome back to Trigonometric. In this video, we are going to be discussing about how to know if a signal has an even or odd signal. In essence, we want to know if a signal is an odd or even signal. Because if you know that a signal is an even or odd signal, before analyzing it, because we will look why we need this, right? In Fourier, before analyzing a signal, if you know that this signal is even, you would not need to do the complete calculation. You already know the answer for some, that actually it is zero. Instead of having to waste your time. So we are going to be looking at um on how to identify if a signal is even or odd signal. Right? Now, the first step to this is that an even signal has even symmetry, and it is symmetrical about the y-axis. That's the basic way you can identify an even signal. It is symmetrical about the y-axis. Here is it graphically. Here is the y-axis, right? Here is the time axis. Here is the y-axis, right? Here is the time axis. Now, if this signal that we are writing here, right, is symmetrical, we are going to draw the signal. If it is symmetrical about the y-axis, then it is said to be an even signal. Here's what I mean. Here's the signal, right? And as you can see, it is symmetrical about the y-axis. Here's what I mean about something be symmetrical about the y-axis. If you take this signal now, here's the y-axis, and you fold it like this. Let me take a piece of paper and let's sketch that out. It's just like we're going to draw a box, right? Here is a box. Here is the y-axis of the box. If I can fold this signal and get the same thing, right? If I can fold the signal and get the same thing, here's the demarcation, and they are kind of meeting together, right? They are kind of same. Then it is said to be an even signal. Take any signal you know of, right? Let me put another signal down. As you can see in this signal, right? This is another signal. As long as I fold the signal and I'm getting the same thing, right? That signal is said to be what? An even signal. Mathematically, an even signal is said to be that if this is the signal x of t, and by reversing it in time domain, you get the same thing, right? You get the point. Here's how they usually used to do it. Yeah, whenever we have x of t, and okay, we want to solve if it is an even signal, we take the function and say, okay, let's use a cosine as an example, because cosine is an example of a sine function. Now let's say x of t is equal to what? Cos x. Okay, if you want to know it is a sine, let's say we'll replace every t with minus t, so cos become what? Minus x, right? Now let's say that minus x, let's use cos as an y is a value. That's what will make it by using a value we can understand it more. Look at this. Let's say x is 180 degree, right? You know cos 180 degree is the same thing as cos minus 180 degree. So in essence, cos negative x is same thing as what? Cos x. And if that's the case, cos x is equal to cos x, then definitely x of t has to be equal to x of minus t. That's the mathematical way of you knowing if a function is sine. But I mean, if you have a visual representation, by looking at it, you definitely know that it's the same way, because what? If it is symmetrical about the y-axis and you can fold it up and get the same thing over the time, then it's said to be what? An even signal. Let's look at the second signal, which is an odd signal. An odd signal has a odd symmetry, right? It is symmetrical about the origin. Here's what I mean. If you have a signal like this, right, which isn't symmetric, it is symmetrical about the y and also the time axis, right? Here is the time axis. Time, here is the y-axis. So if the signal is symmetrical about this and about this, I mean, you can look how can that happen at the same time, which means it does so by what? Doing it like it's just like you are pivoting around the origin, so you can be symmetrical around this and also symmetrical around this, right? So in essence, an odd signal is symmetrical about the origin instead of saying it is symmetrical about the y and time axis. So it is symmetrical about the origin. Another example for an odd signal is something like this. If you have something like this, we have a signal like this. Look at this. It is symmetrical about the origin, right? Look at this. It is symmetrical around the origin, not on the y-axis or on the time axis, but rather around the origin, right? In mathematical representation, as you see, the example of cos, example of an even function is cos x. We have more example of what even function. We have cos hx, like what that is the hyperbole cos inverse. Is it cos inverse? Yeah, cos h of x, right? It's also what another function, and let's say we have x squared, right? Is also what an even function, because you know everything that goes into, even if a negative value goes in, it turns into positive, right? That's another function. Now mathematically for odd function, x of t, when you do the same principle as we applied here, we're going to have minus x minus t. You get the point? For example of what an odd signal is sine, and you know what a sine does. We have sine x cube, we have x cube. You know, these are kind of odd. You know, by having, like, let's say minus 2 to the cube root, it's like saying minus 2 times minus 2 times minus 2. We end up having minus 2 times 2, 4 times 2, 8, minus 8. But let's say it is what? Minus 2 raised to the power of 4. We end up having minus 2 times minus 2 times minus 2 times minus 2. We end up having what? Minus times minus plus times minus, minus times minus plus. So we end up having plus 2 times 2, 4 times 2, 8, 8 times 2, 16. So in essence, you see that we have a positive value if it is even, right? But for odd, you get a point. So that's the mathematical way of representing it. Now, what are we going to use all this for? Its use case is because of what? Fourier, right? And not only Fourier, but since this is a series about Fourier, we need to understand why we need it, right? Whenever a problem comes up and want to analyze it, sometimes it's quite tedious for we to analyze, because in every function, right, every periodic function, for we to apply Fourier series to it, right, we must have some values, a sine value, a cosine value, and a BC value. Now, let's see an example of a signal. We assume that this is a periodic signal. As we said, this is a periodic signal, right? Because it is repeating at regular interval. Now, if you are going to apply one of the technique of Fourier series, as we discussed in the section of Fourier series, we said that we are going to have like three values. We call that A naught, AN, and BN. This is the most important. These are the constant that we are after, we look for, right? Because we already know that a Fourier series or a signal can be decomposed using Fourier series, and we end up having A naught plus summation of AN cosine n omega t plus summation of BN sine n omega t. So if we can know what A naught is, AN is, and BN, we can completely describe what the signal is in terms of several components. So these are the three constants or coefficients we look for. In essence, we look for A naught, AN, and BN. So whenever we know that a signal is even or odd, it makes it easier instead of calculating for this, and this, right? So for instance, in this signal that we just drew, right? If we switch this, if you fold the signal, it isn't even, right? If we fold it, it isn't even, right? Nor we can say, since it is not even, we have component of odd, right? A naught is a DC value, and I will explain how or why this a DC value or A naught value can only exist. In this case, a A naught value will exist, right? But in some other case, a A naught value will not exist. A A naught value will exist for this. AN will not exist because AN has to be even, and this function is not even. But for BN, it will exist, and this also will exist. This won't exist. So in essence, this is equal to 0. Let's look at another signal. Here is a signal which is similar to this, but there's kind of a little difference, right? Now, here's something. This signal has value at the top and also below, right? Which means you can conceptually or intuitively think of it this way, that the summation of the upper part will cancel or will cancel themselves with the lower part. So if the signal exists in the upper side and the lower side of the time axis, if I may see, right, then A naught is equal to 0, because actually we are looking for a constant value or a average value, because A naught is often the DC average value of a signal. In this case, we can have it because we can find it along this side. But this upper part is equal to this down part, and it's going to cancel. In essence, A naught is 0. Now let's look AN. This signal is quite similar to this. It is not even, so this one also is 0. Am I right? Let's look at this. Bn is what is not equal to 0 in this case, right? It is the one that is not equal to 0. There's a component for it. So you see, instead of having to solve for this, and end up knowing that it is 0, waste of time, you just boom, you go to Bn. Let's look at another example. Kind of similar to the same function, right? But there's some quite changes to it. Right. First, what is A naught? I mean, you should know this by now. The upper part cancels the lower part, which means it is 0. Okay. What about AN, bro? Now, AN, I mean, if you put this signal up, they face each other. So if you put the symmetry about the y-axis, which means AN is not equal to 0, which means the signal is even. And if the signal is even, Bn, which is a odd component, is 0. I mean, no doubt about it. So which means Bn is odd, and it is 0. Let's look at another signal. Here is another signal that we can look at. This is kind of like a ramp signal, right? Like a square or sawtooth wave, right? The first thing, it is repeating at the top and at the bottom. A naught equal to 0. If we switch it up, are we going to have the same thing? No. An is equal to 0 because it is not even, right? Bn is what? Equal to 0? No. Pn is not equal to 0, because if you turn it, you're not having the same thing. We kind of think of it as it is what symmetric above the y-axis. Look at this for odd signal, right? So it is not even so. We can have an odd component for this. This is not, right? Let's look at another example. If you have something like this, what can you say about this signal? Looking at this signal, is it even on odd? I mean, by looking at this, it is a sine wave. And as this signal is a sine wave, you know a sine wave is odd. It's kind of conceptual. You can think of this way. Just know that a sine wave has what? A odd symmetry. Well, a cos has a what? Even symmetry. Because here is a cos. It goes this way. Look at this. Right? This is a cos, which is equal to what? Even function. Here is a sine, which is equal to what? Odd function. I hope the concept about trying to know if a signal is even on odd is quite simple, right? Or understandable. If there's any question, as usual, feel free to share it in the comment section, and I'll be there to respond. Thanks.